My name is Johannes. I'm here with Joseph, Giorgis, Stefan, Hamilton, and Chile to present our work on OpenMP-Aware parallelism optimizations in LLVM. And we're going to start by talking about OpenMP and LLVM in general. Hi, everyone. My name is Johannes. Together with Joseph, Stefan, Giorgis, Hamilton, and Chile, we're going to talk about OpenMP parallelism in LLVM and how we started to make LLVM parallelism aware, especially with regards to OpenMP, but we'll go a little bit more generic in the end. When we talk about OpenMP and LLVM, there's a couple of things to say first. OpenMP and LLVM was classically considered like the Clang part. So the OpenMP parser, the OpenMP semantic analysis, and the OpenMP code generation. And that was mostly what was associated with OpenMP and LLVM. Arguably, the OpenMP runtimes that LLVM ships with are also OpenMP and LLVM under like the umbrella LLVM system. So there are 3 runtimes actually, or a couple of more depending on how you look at it. There is libomp, which is the classic host runtime. There is libomp target and the plugins, which integrate GPU architectures and other accelerators. And there are the device runtime libraries, which are actually shipped and executed on the accelerators, not on the host. Now, we're moving towards a Fortran frontend that is OpenMP capable. So the new Flang is going to be OpenMP capable as well as similar to Clang. So we are now having 2 frontends that have OpenMP parsers, OpenMP semantic analysis, OpenMP code gen, and that brings new challenges and opportunities. One of these things is that we started to develop an OpenMP IR builder, which translates OpenMP directives, more or less, into LLVM IR. That way we can reuse all the code generation part of Clang in Flang, and we can also use this from other languages that basically want to lower to OpenMP parallelism, like the OpenMP runtimes, the OpenMP target offloading, but without actually going to an OpenMP front end like Clang or Flang, but from their language. But today we're actually talking about the newest part of OpenMP and LLVM, and that is OpenMPOpt, which is an LLVM pass that was added recently. It is actually enabled by default since LLVM 11 when you run with O2 or 3, and it contains a few, but not that many, host and device optimizations. So for both your classical OpenMP host code, but also for your GPU code that you do with OpenMP target offloading, we're actually going to apply optimizations. And today we're going to introduce design goals of OpenMPOpt. We're talking about things that work already and things that are going to work eventually. And we're split it between the different people that work on this. And as you might have seen in the top left corner, I have a short link to our weekly meeting, which is something you are invited to join. We discuss OpenMP implementation things in Clang, in the runtime, in the OpenMPOpt pass. And we're happy to have more people that help us here and that bring in ideas and work power. Okay, that said, let's start with Joseph.
Hey, I'm Joseph Huber, and I'm from Oak Ridge National Lab. And one of the central design goals we had when working on OpenMPOpt is to report as much information as possible to the user. This way they'll get as much information to know about what transformations the compiler is doing and what transformations they don't need to be doing, and also what is even available for the compiler to be doing. So to show this, a simple example of an optimization we support is runtime call deduplication. So this code example here is just a short snippet that you might use if you wanted to allocate a size memory buffer for each thread when running something in parallel. So we call the runtime function OMP get thread limit, which simply returns the maximum number of threads that can be in the current OpenMP parallel unit. So we use that to allocate memory for each thread, and then we can run those in parallel, given the thread number. So ideally, we could have Clang or the compiler merge these runtime calls because they're going to output the same value when you call them like this. But Unfortunately, these functions are completely opaque to the compiler because they're just calls into a runtime library. It doesn't know anything about the semantics or the fact that they're read-only and can easily be deduplicated. So to combat this, we added an optimization to deduplicate them in OpenMP-Opt. And what this does is maintains a table of functions that can be deduplicated, and it simply scans all of the usages of runtime calls, sees if it matches. If it finds one, it moves it to the top of the current code block and removes all references to the runtime function and replaces it with that one. So even though this is a relatively simple optimization we can do, we still want to report it to the user because this is something they want to know. For example, they don't need to be manually getting the thread limit and then calling malloc to optimize it. And it also shows them that this is something that's being done. It also gives the ability for tools to use this information to gather statistics about what's going on with OpenMP-Opt and which runtime functions are very commonly deduplicated. And you can use this information for any of the optimizations we do ideally. So this just shows how to trigger the optimization remarks for this small example. As we mentioned previously, O2 runs it by default, and you pass in rpass OpenMP-Opt. So you're telling it to print out the optimization remarks for OpenMP-Opt. And if you run that, you should see these two examples. So this kind of leads into another problem with OpenMP, is that its implementations are very opaque. OpenMP allows the user to communicate parallelism and other things to the compiler. I can say something runs in parallel, and the compiler takes that block, puts it in a function, and then inserts a runtime call to fork. So each thread runs that function in parallel. But the user doesn't really know what's going on behind the scenes, and in many cases, this can have very large performance implications. So especially because OpenMP is commonly used for scientific computing and high-performance computing applications. So an example where this is relevant is simply scheduling parallelism across a simple, two-nested loop. So in the first case, we distribute the parallelism across both using the collapse clause. So we're distributing it, this whole loop nest across both the blocks of the device and the threads of the device. In the second case, we distribute the first loop across the blocks of the device, and then for each block, we distribute the threads of that block across the second loop. And there's a pretty stark performance difference between the two, and it wouldn't be, directly obvious from just reading this, because they're going to be implementing relatively similar levels of parallelism. And the thing you'll find is that the first case has good performance, whereas the second case has bad performance. And this isn't obvious, as mentioned previously, because the parallelism should be doing similar things. And little caveats as we're optimizing this out. And the reason for this is because the first example can take advantage of what we call SPMD mode. And what this does is it evenly distributes the work among the blocks and the threads on the device. So we don't need to instantiate any extra logic to manage it. We simply say each iteration of this loop gets a thread inside many blocks. The second case, however, is using a split mode, which needs to use what we call generic mode. This instantiates a state machine and uses extra registers to hold call edges, which schedule the threads within a single block. And this introduces a lot of overhead and removes the ability for doing some extra compiler optimizations. And this isn't something you'd find in an OpenMP manual, because this is clearly something that is just relevant to the compiler implementing it, but it can have large performance implications. So we support printing out some remarks for this already, but as you can see, this is kind of difficult to read, and if you don't know what any of these words mean, it can get very complicated. And in order to sufficiently explain these things, a terminal output using remarks is not the best way to do it. So moving forward, we're going to start maintaining a website that has different pages that you can refer to, and the remarks will tell you to refer to this ID to get extra information out of it. So we can change these to just give you some basic information about what the problem is, and then you can get additional information about the runtime implementation or whatever problem you're running into at the website location. And another thing we've been working on recently is giving support for the runtime library to print out information about how the function is actually being mapped onto the device. So previously you could only get this information if you built a libOMP target with a debug build. And many users don't want to, deal with the overhead of a debug build, and even given that the debug functionality is mostly for the developers and not the users. So we've been adding support for information dumps that use an environment variable called libOMP target info. And this is supported right now, that you can use this environment variable and hopefully get out some useful information about what your function is doing. And next is Stefan.
Another important design goal for the OpenMP-opt pass is the ability to write modular OpenMP code without performance penalty. So in other words, we want to embed the domain level knowledge so the others don't have to worry about it. One way of doing that is through ICV tracking. ICV stands for OpenMP Standards Internal Control Variable, which controls the behavior of OpenMP program. This ICV stores information such as the number of threads to use for future parallel regions, the schedule to use for work sharing loops, and whether nested parallelism is enabled or not. In the next few slides, we'll demonstrate how ICV tracking can be used. So consider the following example. We want to be able to write modular code. However, we don't want the potential nested parallelism here. As a result, we end up with the following implementation, where we do different things depending on whether or not we are in the parallel region. With the ICV infrastructure, we can remove the checks to the OMP in parallel call if it is known to return true. This will potentially result in performance improvements. In general, ICV tracking allows us to replace runtime calls with known values, use known values for other optimizations. And so, as you can see, it's not only about deduplication, but rather about computing the return value. It's also important to note that we are doing the tracking interprocedurally through integration with the Attributor. This allows us to take the full advantage of the Attributor, and such as fixed point iteration, multiple IR positions that we can track the values for. Also, this is not strictly limited to ICVs by the OpenMP standard. We can track an arbitrary state that has getter-setter pair. For example, we can track if we are in SPMD region, which is an implementation-defined state.
Hi, my name is Georgis Georgakoudis, and I'm a computer scientist at the Lawrence Livermore National Laboratory. I will be talking to you about another optimization that enables OpenMP code modularity with high performance. And this optimization is called parallel region merging optimization. And the pattern that it targets is that of consecutive OpenMP parallel regions, and the optimization merges those into one large parallel region. So the motivation behind that is to save OpenMP runtime overhead. So every time a parallel region starts, the OpenMP runtime needs to activate a number of threads and then reach an implicit barrier. By merging regions together, you save some of this overhead. So in this example, you activate the threads only once. The other motivation behind this optimization is that by having larger parallel regions from merging, you also enlarge the scope of other OpenMP optimizations, like, for example, runtime call deduplication. We do this work in the LLVM IR, and we also support more complex patterns. So, for example, if there are parallel regions that have some sequential work done intermediately, then we also support that by merging them safely and emitting extra code to make sure this sequential work happens by one thread, only when this is unsafe to run in parallel. So that's it for me. Thank you.
Hello, everyone. I'm Hamilton, and I will be explaining one of the optimizations we're working on. What this optimization tries to do is to hide as much as possible the latency incurred when transferring data from main memory to a device's memory, namely a GPU. We do this by replacing the original data transfer for an asynchronous version of it, and the wait directive for waiting until that transfer is finished. We move the asynchronous version of the transfer upwards in the function, always making sure that the instructions it is moved over don't modify any of the data being transferred. And the wait directive is moved downwards in the function until a target region that needs that data is reached. But in reality, it looks more like this. Since at the IR level, we only handle runtime calls, we replace the runtime call of the data transfer for an asynchronous version of it that returns a handle. And that handle is used later in a function that waits on it. So when this target region is reached, hopefully the data will already be in memory, saving up a significant amount of time. Another nice use case is avoiding unnecessary data transfers. So for example, in this case, the user has two data transfers and some computation in between. Each of these data transfers sends the data to the device, and after the target region is finished, it requests the data back from the device. So if this computation in between doesn't modify any of the data, the user would be wasting two transfers. Why? Because after this first target region is finished, the data is requested back from the device. And then in this second target region, the data is sent to the device. But why if it was already there? So if we apply the same principle as seen before, requesting the data from the device in this first data transfer can be split into an asynchronous request and wait until that request is finished. In this case, the wait is moved downwards until it reaches the second data transfer. And we can see that this data transfer needs the data in the device. So we can conclude that if we don't request the data, this data doesn't have to send it again. So we remove the request from the device in the first data transfer, and we remove sending the data to the device in the second data transfer. So avoiding two unnecessary data transfers. So hopefully saving a significant amount of time. And basically that's it.
Thanks, Hamilton. Hi, I'm Shilei, a PhD student in Stony Brook University. Today, I'm going to introduce the heterogeneous LLVM IR module, which enables combined optimization of host and accelerators. I will use two simple OpenMP examples to show why do we need it and how it can help. Please keep in mind that other languages like CUDA, SQL, HEAP basically behave the same way, so it is not specific to OpenMP at all. Let's say we just have one target device, so clone will compile the source file twice and generate two individual modules. One is for host and another is for device. Here I'm using pseudo C code for simplicity. So in the host module, we call the function offload to do the offloading job, which corresponds to the OpenMP runtime library interface. And if it fails, a host fallback will be executed. And on the device side, this function is the one that will be executed by GPU threads. Let's do some optimization on them. And let's use the simplest version, constant propagation as an example. So every use of n in the host module will be replaced by its value, and the definition of n can also be removed. However, its value cannot be propagated to the device module, to the device function, because the constant is part of the host code and optimization cannot cross modules. So the device module does not know the existence of the constant at all. We need somehow to pass this information to the device module, and that's why we propose the heterogeneous IR module. With heterogeneous IR module, the host module and device module will be merged into a unified one. And in order to tell the symbols in host module and device module, a target attribute is attached to each global symbol. For example, here, target 0 is attached to the function foo, and target 1 is attached to the function, to the device function. Of course, we can have multiple targets. There will be target 1, target 2, etc. And target 0 is always for the host. What's more, we also add a callback attribute to the function declaration of offload, which corresponds to the LLVM's offload metadata attached to a function declaration. In this way, we establish a connection from the host function to the device function. And when we do optimization, the information that n is a constant can be also propagated to the device function. And we don't need this kernel argument anymore, and there is no memory load in the kernel either, so which can improve the performance. The previous example shows how the heterogeneous IR module can help with information shared from the host side to the device side. And now let's look at another example to show how the information can shared from the device to the host to guide the optimization on the host side. Now we have two arrays, A and B, and in the target region, we just assign elements from one to another. And like before, we have two individual modules. Actually, when we call the function to do the offloading, we actually pass another argument to it. And one of them is to tell what the map type of each kernel argument is. According to the OpenMP specification, if we didn't specify any map type, by default, it will be to from, which means data will be copied from host to device before the execution and copied back to host afterwards. But if we look at the device function, we can see that we only write to A and read from B, which means we don't need to copy data from host, copy A from host to device before the execution and copy B back to host afterwards. But on the host side, we cannot know this information. With heterogeneous IR module, this information can be shared from the device side to the host, and now we can override the map types and change A to from and B to to. The examples we show here are very intuitive, and we expect to get better results from existing optimization paths. And what's more, we can also come up with more fantastic optimization accordingly. So that's it from my side. I'm going to hand to Johannes. Thanks.
I'm back to conclude our talk by going from the current design goals that guide us while we develop OpenMPOpt to the future design goals that go beyond OpenMP. So if we look at a list of things that we covered during the talk, during the last 25 minutes, you see that we can take all of this and we can easily make it not a recap, but a future work section by just starting to cross out the word OpenMP. So we want to deduplicate not only OpenMP runtime calls, but all kinds of runtime calls. We want to build an infrastructure to get user information through assumes and process it, but also provide the user extended feedback. We want to be able to track hidden runtime state, but also non-runtime state interprocedurally, regardless if it's OpenMP or not. We want to use our OpenMP parallelism-aware optimizations like barrier elimination and parallel region merging for other languages that have barriers, that have fork join parallelism, and later on, once we have task optimizations for other languages that have tasks. And finally, all the languages that do offloading, that do accelerator programming like CUDA, HIP, and SYCL, they will directly benefit from our improvements, our optimizations that we're doing to hide the latency of memory transfers and to allow host device optimizations where you have to look at both the host and device code and modify the host and device code at the same time through heterogeneous modules. I hope you liked our talk, and I hope you have questions in the Q&A, and feel free to join our weekly meeting. Thank you.
Hi, my name is Ravi Narayan-Swamy, and now we're moving on to the QA session. I'll be a moderator. So I'm going to start off with, first and foremost, I want to thank all the presenters. That was wonderful. Now I'll start off with the first question. Many of the design choices you made are similar to the MLIR. Example, progressive lowering, better debugging, error handling. So what's the reason for not choosing MLR and having your own MIR? And I think I'll go with Johannes for this.
Right, thanks. So first and foremost, it's practical. Like there's no reason not to assume that we couldn't move the logic that we're building to MLIR. At the end of the day, it's kind of a representation. If we match a runtime call and say this runtime call does the following thing, and the arguments to the runtime call have the following semantics, we could just as well do that with operations in MLIR and the arguments to the operations. It's an encoding difference, but it's not like the semantics of a runtime call would match the semantics of an op. So it is really just what is your encoding you're working on. And after you realize that, it's a practical matter. We already have these runtime calls. They work in Clang. We have this pipeline up and running, and we actually want to provide people with a working optimizations now. We have explicit tracking of memory of locations as part of these runtime calls already now. So which is different to like the debug metadata in LLVM IR, but there is a special location tracking mechanism as part of the OpenMP runtime. So we have debug information and error handling information already available. So we don't actually need to kind of improve on LLVM IR. So it is first and foremost a practical choice. And it gives us the ability to build these things, to develop and design these optimizations, try them out on Clang without having to wait for the entire MLIR stack to mature, and gives benefits to people right away.
Thank you, Johannes. Okay, the next one. If you have a heterogeneous module, how do you handle module details like data layout? Shall I? You want to take this?
Shall I?
Yeah, can you hear me?
Yeah, now we can.
My internet is not stable. Sorry. Basically we will have identifier for all the global attributes for all the symbols. So when we optimize all the let's say procedures, we will only work across with them with the same attributes, like the same data layered sort of things. Yeah.
Thank you. So the next one is, when optimizing data transfer, how do you guarantee that the data is not touched in between target regions? Does it work for a single compilation unit? So that's two-part question. The first one is.
For the first one, I think even if we have the heterogeneous IR module, so we can optimize them, like we can get information from host and the device, yes. But if they are in different compilation units, even with heterogeneous IR module, they will not in a single module. So we cannot get that kind of information, so we cannot optimize it. And maybe we can do that in LTO or sort of physics. So yeah.
Thank you. So The next one, how will TTI work for passes that operate on heterogeneous modules?
Let me, as with everything in heterogeneous modules, everything that lives in a global level has to be attached to one module. It has to attach to one target. So you have like these different targets in your heterogeneous module, and everything has a target identifier. So if you want to know something about, like ask TTI something or want to know something about the target, you always have to parse the target identifier, which if none is given, kind of like same as the address space, defaults to 0, which is just the default one. And if you have an address space, you have a different number. If you're actually, this is part for a device, then you have a different number, and then you provide that number to TTI. And that way you get like the right information for your target.
Thank you. So here's one for you, Joseph. Is there currently any available document of all the optimization remarks in the meantime before you create the website with all the info?
So the answer is no. That's why we created the website. I will say we emit them for every single optimization pass we do. And most of them are supposed to be self-explanatory, so you don't need much documentation about them. It's still a work in progress. We're adding a lot of stuff every day.
Thank you. Okay, the next one is, have you run into difficulties with OpenMP standards such that you like to do optimization but cannot do because the standard is too vague or permissive or similar? Okay. Who wants to take a stab at this?
I can make a try on that. For example, in the parallel region merging optimization, if you look at the OpenMP standard and how it defines how to do processor affinities using the procbind, call, it basically makes the user give specific affinities to threads on a parallel region. And when we were doing the merging and reading the standard and trying to adhere to the standard, although some parallel regions could be merged by avoiding or sidestepping over those processor binding affinities, we decided not to do that and follow the standard as much as we can. So optimizations need to be safe, and also they need to be within the standard specification. That's my experience with that.
Okay, so when doing parallel, do you find when you're doing parallel optimization, do you find that lowering to LLVM has removed some high-level information which could be useful, unnecessary, and how do you handle it or plan to handle it?
Yeah, I'll take that one. Okay, have we lost information? Sometimes, maybe so far in the transformations we wanted to do, that was not yet a problem, but there certainly are lowerings existing that would lose too much information and we would have to revisit. The main problem with the lowering is not that we lose information, because if you don't want you lose information, just don't lose it. Like we're generating runtime calls at the end of the day. And you can encode everything that you have at the high level in those runtime calls. There's no need to lose anything. That said, the main problem that we've encountered is when the front end does lowering that is too, let's call it complex. Instead of calling a runtime function that says, do this, it starts to do conditionals, say, okay, if I'm in this special case, I can do this kind of transformation, I can do this kind of optimization early on, and so on and so forth. And once you're down that rabbit hole, the code that you generate that is kind of a lot of, that has complexity in the user module, that you can't optimize properly anymore, because it's hard to undo these things. Instead, what we opted for, and that what we are propagating, what we're currently doing, is to move this complexity, this logic, into the runtime, and then just use arguments for the runtime functions to choose which behavior you want. Like you want a special case 1, and then pass the number 1. If you want special case 2, pass number 2. And if you don't pass a number, you get the default implementation. So you hide all that complexity away. That makes it way easier for any IR pass to analyze this thing, because it sees the runtime call, it knows what it means. It might know about the special cases, which at the end of the day are special cases anyway, and you can deal with that. So long answer short, we haven't encountered missing information yet, and if we do, we will add it as part of the lowering in Clang such that it's not missing.
Yeah, so I think we run out of time, so I want to thank all the presenters, and thank you all for joining the session, for submitting your question. We encourage you to continue the conversation in the community board of WUA or in the roundtable sessions. Thank you.